Assalamu alaikum. My name is Hana Shamayleh from Qatar University, and I will present our work on dynamic characterization of layered ground from vibration measurement. This study focused on identifying the stiffness, thickness, and damping of layered soil profile by matching measured or reference vibration responses with a numerical model. In this presentation, I will first introduce the motivation and problem statement. Then I will describe the methodology, including the layered half-space model and the parameter estimation procedures using least squares regression and genetic algorithm, followed by key results and concluding remarks. Accurate geotechnical parameters are essential for predicting soil behavior under dynamic loading and for a safe earthquake-resistant foundation design. However, direct measurement of elastic modulus, Poisson's ratios, layer thickness, and damping in layered ground is often impractical or too expensive. So, using inverse analysis based on dynamic response becomes an attractive alternative. Actually, in this study, a two-layered half-space is considered, and both least squared regression and genetic algorithm are used to estimate elastic and geometric parameters by matching computed and reference frequency domain displacement responses. The estimation process is carried out in two main steps. First, a reference dynamic response is generated using a forward model for a prescribed set of soil and layering parameters. Secondly, using the same forward model, either the least square regression-based search or genetic algorithm-based optimization is applied to identify the soil parameter that is best produce the reference response in the frequency domain. In this slide, we will see the two-layered half-space configuration used in the forward model. So the upper layer represents compacted silty sands. Underneath it, we can see a stiffer half-space that can represent dense sand or weak marl, which is typical of many sites in Qatar and Gulf region. So there is a vertical or surface vibration is applied, and the resulting frequency domain displacement response at the surface is used as the measured quantity for the inverse analysis. After finding the reference response, from now on, we will say that we don't know these parameters. We will take this calculated response as a measured amount. These unknowns can be determined using the least squared regression as a first step between the dynamic response using the tested values and the unknown values. Here, the main steps, the other way or the other method that I have used, the main step of the genetic algorithm are summarized. So, an initial population of candidate soil parameter set is generated, and the fitness of each candidate is evaluated using an objective function that measures the error between the computed and reference frequency responses. Through selection, crossover, and mutation, new generations are created and the process continued until there is no further significant improvement, at which point the best individual represents the estimated soil parameters. So this is the case that we use. These are the parameters. The top layer assumed to be compacted silty sand, and here is the value for its parameter, and the underlying half space representing dense sand or weak marl, and here is the parameter that we have used. Okay, so in this slide we will see the least squared regression profiles for the estimated parameters. we can see that each profile exhibits a clear and well-defined minimum at the true parameter value, indicating that the inverse analysis successfully recovers all 5 target soil properties, in which the response is noise-free and the model is well-posed. Okay, here we can see the 3-dimensional LSR surfaces that demonstrate how estimation accuracy varies within the parameter space. So, for example, E1 and E2 exhibit the strongest influence, which is steep gradients and sharp minimum, which means that the surface response is highly sensitive to the stiffness and thickness of the top layer. For example, E2 shows moderate sensitivity, while the Poisson's ratios nu1 and 2 produce flatter surfaces and are less influential, suggesting that they are harder to estimate uniquely and may require additional constraints or prior information. Here we can see the genetic algorithm-based parameter estimation results. The frequency response computed using the genetic algorithm estimated parameters shows excellent agreement with few errors with the true response over the full analyzed frequency range, confirming that the genetic algorithm successfully recovers the dynamic soil properties. The convergence history indicates that the genetic algorithm achieves rapid improvement and stabilized within about just 11 generations for this problem. So in conclusion, both the genetic algorithm-based optimization and the least square regression-based investigation accurately recovered soil layer stiffness, Poisson's ratio, and thickness with very small error in the frequency response domain, confirming that the adopted forward model and the objective function are well suited to this inverse problem. The least square regression approach provides clear insight into the objective function landscape, but required about 1,200 minutes, like in a high processor CPU time, whereas the genetic algorithm converge in roughly about 20 minutes for the same problem and same device, making it a far more computationally efficient options. So future work, we will focus on applying this framework to real experimentally measured responses and extending the set of estimated parameters, especially for damping for practical site characterization.